Hi there, this is Laurent Kneip, and through this video I'd like to introduce one of our recent works entitled RGB-based category-level object pose estimation via decoupled metric scale recovery. Our work is about accurately determining the position and orientation of an object in 3D space, which is a critical task in many environment perception and robotics applications. An established approach consists of predicting pixel-level normalized object coordinates, or in short NOCS maps, to identify the 3D points in a canonical normalized object reference volume that correspond to certain camera points. The method operates at category level, and the final object pose is obtained by generalized Procrustes alignment. Promising results have been obtained by RGB-based methods, which do however depend on depth observations to recover 3D camera points and in particular achieve accurately scaled pose and size estimations. Pure RGB-based category-level object pose estimation methods have also been presented, and they are necessary on compact devices where depth readings are not available, for example VR headsets or mobile devices. Recent methods simply propose to apply image-based absolute depth map prediction, which thereby transfers the problem to the familiar RGBD setting. However, image-based depth prediction suffers from inherent scale ambiguities, leading to inaccurate and unsatisfactory results. Unlike existing RGB-based methods that expect to implicitly learn the metric scale through absolute depth prediction, we instead choose to decouple object pose and size estimation. The motivation behind this choice is that we want to explicitly cut off the propagation of errors from absolute depth predictions to 6D pose estimation, especially for rotation. Rather than using Procrustes alignment, the method therefore relies on 3D-2D alignment between normalized object coordinates and image points. We use PNP-RANSAC to robustly solve for 6D object pose. The pipeline mainly consists of 4 parts. The first module performs feature extraction and uses the image, a category-level shape prior, as well as predicted 2.5D sketches, meaning rough depth and normal maps, to extract higher-level features for 2D-3D correspondence learning. The next module extracts 2D-3D correspondences, which is realized by predicting both a deformation field for a shape prior and a correspondence matrix. This returns the NOCS coordinates. A separate branch for metric scale recovery is added, which is essential to scale the deformed shape prior. The final module runs PNP-RANSAC to recover the pose from 2D-3D correspondences. Here we can see examples of generated 2.5D sketches which represent rough instance-level geometric information such as depth and normal maps obtained from input image patches. The figure shows examples for 6 categories for both the camera and the real dataset. Here we show some qualitative comparisons of predicted depth maps and ground truth depth maps. On the camera dataset, predicted depth maps faithfully preserve geometric structures and contours around each object instance. On the real dataset, the ground truth depth maps are easily affected by sensor noise, illumination conditions, and spatial materials, while the predicted depth maps maintain comparable performance to the synthetic case. Note, however, that object contours tend to become slightly blurred due to cluttered backgrounds and shadows. Finally, we obtain qualitative results as shown in these examples. The estimated object pose and size are visualized via projected 3D bounding boxes in red and object coordinate axis. Ground truth bounding boxes are indicated in green for reference. As can be observed, our method is able to generate tight bounding boxes around objects, thereby reflecting faithful metric scale recovery. Moreover, the prediction remains highly consistent across different categories. Here some further video-based results. Note that in those videos each frame is processed independently, which therefore showcases the high robustness of our method. In terms of quantitative results, we compare our method against MSOS and OLDnet. We evaluate percentages of results that achieve higher than 0.5 or 0.75 intersection over union, or less than 10 centimeters or 10 degrees positional and rotational errors, both individually and simultaneously. As can be observed, our method significantly outperforms previous RGB methods in terms of rotational accuracy, demonstrating the strong potential given by correspondence learning. For the positional and 3D IOU metrics, our method also achieves competitive results, especially for the strictest IOU 75 metric on Real 275, where our method outperforms the next best method MSOS by 3.1%. The combined improvements in rotation and translation accuracy in conclusion lead to strong improvements in the combined metric as well, outperforming OLD net by 4% and 13.8% on both datasets respectively. We further present a more detailed analysis of the average precision for different categories and error thresholds in terms of the 3D IOU, rotation and translation errors. Generally speaking, the performance on ICRA'25 is better than Real 275, which is related to a lack of training data and cluttered backgrounds in real scenarios. Further ablation studies can be found in the paper. And that's a wrap for this video. In conclusion, we propose a decoupled framework for RGB-based category-level object pose estimation, where 60 object pose and size are computed separately to reduce the negative influence of imperfect scale predictions on rigid transformations. Our code is publicly available on GitHub, and our dataset can be downloaded from Google Drive. Thanks for listening, and we look forward to engage in further discussions with you.